Today we will talk about ownership and Structs. This talk is strongly inspired by the Rust book fork of the Brown University. So we will see some diagrams and graphics from them, which are very nice. My name is Tim Janus, and I'm really presenting this and try to explain it in a way that helps you to understand this it's a complicated topic, and we're here to help. So if you have any questions, feel free to reach out. So it's the second part. Last week, Kira gave the setup, and next week, no, I think on the 25th, Cosmo will do pattern matching, right?
Indeed. I'll be talking about that.
What we will not cover is how to start programming. So it's best if you're aware in another programming or language already. And we won't cover really advanced concepts, but we want to help you if you're from another language to learn Rust and make those huge amount of learning materials more accessible. So for today's talk, we will start with kind of a history 101 to get a feeling how Rust was or was motivated by a former programming language. Then we will talk about the stack and the heap as uh, how the computer works with memory. So we talk about what is ownership, and strongly related to that about references and borrowing. Many people may have heard about the borrow checker. That's where this part comes in and helps you or annoys you at the start with some error messages. But hopefully at the end of this talk, you feel equipped to go hunt down those errors on your own, know what you have to do. And we will conclude with a small recap on slice and introduce data structures like you know them from other programming languages. Okay, first things first. So when you come to Rust, the key selling point is safety. And to define safety, you have to hear about what is undefined behavior. And normally you have undefined behavior if code is executed, that that behavior is not fully specified. That can happen, for example, in some specifications like the C++ standard. And then that depends strongly on the programming language. And in C++, you can compile programs that lead to undefined behavior. But the nice thing is in Rust, if there would be undefined behavior, it won't compile. Or the other way around, if it compiles, there's no undefined behavior. And yeah, for our History 101, there's a small example program. So we have a main function. And what we do here is not commonly seen in Rust code. That is, we declare a variable without bounding it to a value. And for this, we will then get a compile time error when we want to access the variable. So this program won't compile. If you come from a different language like Python, you could have a similar program where there's a variable without a value, so not defined yet. And then you get an error at the runtime when you execute the code in your interpreter. Because of this runtime checks, that's one reason why those languages are a bit slower. And when you go further back in time in C, people normally cared more about performance and being very expressive. And so you could just declare a variable, and then it's quite random what is in X now. So if we walk through this code, we call the function readX, and then we check if y, that integer is probably not zero, so it is seen as true. But then if you print out the actual value, this number here, this y would change which whatever is on your processor. So that could be y is 1 million on the one computer or minus 1 million on the other one. And so That's like the basis what undefined behavior looks like. And it's most dangerous when you combine this with low-level memory operations, asking for memory or accessing it at the wrong parts. And Rust's foundational goals is first ensure there is never undefined behavior, and to prevent that at compile time instead of the runtime. So you get this more safety guarantees, but at the same time you get a blazingly fast binary. And I I was a bit poetic and come up with a small rhyme here. So C invites demons with freedoms so wide. Python guards safety, but checks at runtime side. Rust blocks the trouble before it can start. Compile time strict, yet performance apart. And well, our goal is to understand how Rust enforces these guarantees. And therefore, we have to understand a bit about how memory is organized for programs. So that will give you some theory background, but we will also see actual code with these error messages to equip you to fix them. Okay, so when we talk um, about memory, some notifications here. When we talk about memory, it is normally separated in the stack, and there you have several frames that are linked to a scope, like a function or if-else blocks. And there are data types like string and vec that store a so-called pointer into another memory area and metadata on the stack. We will come back to that later on, but especially string and vec are the types you're mostly using. And now to give you like an illustrative example, that's actually from the book I mentioned, from the fork from the Brown University. If you have a main function here and you define a variable n, and at that point in the program, the stack would look like, okay, there's a frame for the main function and n is 5. And later on, if we go to the next line, you can see there's a function call. So we hop into this function, and in the function, you see another place, L2. And at L2, we have one frame for the main function and another frame for the +1 function. And here, the argument of the function is still 5 because we are on the left side here. And when we then return this um, calculation +1, we have y with 6 on the stack frame in the main function. And the heap is more for really dynamic memory when it has to outlive like a scope. And it is either managed manually, often in the C programming language, or in newer standards, there is a standard library with so-called smart pointers. Or in other languages, often like systems are used like garbage collectors that um, free up the memory when there are no references to this memory anymore. And there are built-in types in Rust um, that uses heap too, that is string, and the vector type, so the dynamic resized array, for example. Another type we will see later is a box T, which just stores some type T on the heap. Um, yeah, I see there's a question. Probably yes. So if you look into the assembler code, that would happen. But for our model to not introduce another layer, I think it's good to have this look. So it's in the end a model on the memory layout. The intrinsics may be more complicated still.
Yeah, in a sense, you can view registers as being like an optimization of the broader model, which is just some objects are on stack frames, some objects are on the heap. And if you have a small enough amount of data, you can take some of the things you have on the stack and put them in registers. But in terms of the memory model of Rust, it's on the stack.
Well said. Um, so yeah, I already mentioned those most common Rust types that uses the heap, which are the dynamically sized array of elements T, like a vector, or the string, which is also a dynamically sized array, but of UTF-8 characters. And this basic Rust data type, I let it in here because some of you may have a C background, and that is actually the unique pointer in C++. Or from a conceptual perspective, you can see it as a owning pointer. So the pointer really owns the data it is referring to. And this box has this shared properties with the string and the vector, that there is some metadata, in the case of the box, just a pointer on the stack, and the inner or dynamically sized data is put on the heap. And here's an example for the heap itself, a small one, where we have A on the as a variable on the stack, which is a box, and this contains this pointer to the heap of the data. So what this expression means is we generate an array of zeros with a size of 1 million. And for other types, there may be more metadata on the stack, like the lang and the capacity of the dynamically sized data. Um, Now to come to this concept of ownership, it is a particular way of thinking. So at every point in time, one there's one unique owner of a piece of data, like one variable owns the data. And um, that's very important to keep that in mind. That means most often if we use a assignment operator, like here, there was a second line with let b equals a. What happens internally is like this heap data got moved. So A got moved into B, and A is from there on not accessible anymore. And that is the default in Rust. And when you have some example code that you could find in your own program, for example, you have a name, Ferris, and you want to save the name in another variable. Here, you cannot access the first variable anymore because it was moved out, and um, you get like this longer error message. But let's go through this step by step. So what happens here? This last line, println, tries to borrow a moved value called name, and then the compiler comes with some reasoning behind that. And first of all, why did it have been moved? Because it's a string and that doesn't implement a copy trait. So copy is not default. You have to opt in into copying data. And then it shows you the line where the value has been moved and where it has been borrowed after the move. And it also gives you a tip to maybe clone the data, which is a deep copy instead. And I think that's very helpful if you're not let's say scared by these long messages, but really try to go through them one by one. Also with the theory we will come up with here. And yeah, as always, to a default rule, there are always exceptions. There are copyable types, like all the scalars, like integers and floats, are normally copyable. And that's true normally for really small data types where you fit them in small amount of bytes, then this code works totally fine. So don't get confused too much by that. That's the reasoning behind it, that you have an exception for small built-in types. And so to illustrate what happens when you use this deep copy called cloning. So here we have a function, a main function that has this Ferris string, and it also generates first clone by calling the clone method. And now we're here at the L1 place for the stack. And as you can see, we really have the data 2 times on the heap. So the memory is used 2 times at that point. But you can come away with you can yeah get away from some problems this way. And in the next line, we call a function that adds a suffix. So to say this is Ferris Junior. And for this, we um, take in the string. So we move it in here. We push the suffix, and then we return the string and move it back out. So first clone got moved into full in this line. That's also what we see in the illustration for L2. So that's I think quite helpful to understand what's happening under the hood in a simplified model. And the good news is when a variable got dropped, so that means it's leaving its scope. Its heap data is automatically deallocated, and so you don't end up with some memory leaks as you could do in yeah.
We have a question. Is clone really a deep copy? By default,
Mm,
like in the vast majority of cases you'll ever encounter, clone is indeed a deep copy. So clone on strings, clone on vectors, these things are deep
yes.
copy. And particularly uh, Rust has facilities for automatically making types clone. If you do it the way Rust makes it easy, that will also be a deep copy. There are a small number of types in Rust where clone is not a deep copy, and these are reference counted types. But that is sort of out with the scope of this particular talk. And so if you just sort of assume a clone is a deep copy, you will be right almost every time. Is that a satisfying answer?
Yeah, I think um, it is really important for these reference counter types. Mhm. So yeah, maybe that is an interesting use case um, for later talks. Yeah.
Yeah,
Mm,
probably we will bring this up and go much deeper in on it sometime in some later talk.
yeah. Um, to shortly go over this illustration here, what's happening is this variable make and drop, which has a pointer on the heap, it just gets really cleaned up afterwards. And that's working with all the standard types in the Rust ecosystem.
Yeah. C++ people familiar with RAI. This is the same thing.
Yes, like it's like you're using a unique pointer, for example. This has this automatically clean up by yeah by the destructor called in C++. Um, yeah, to summarize that a bit, like the variables first use always the stack, and some types like string and rec also use the heap, and then there's something like a pointer involved. internally. Rust or Safe Rust, in Rust, normally you don't use a real pointer, but references. And this box T is an owning pointer to data on the heap. Safe Rust does not allow manual memory management. Just like, yeah, it's not your task, so to speak. And the owning scope cleans up all these memory elements on the heap. And also, at every point in time, there's only one unique owner of a piece of data. But you can have references, and there may be either one mutable reference, therefore it's also often called a unique reference, or there are many read-only references. And for the borrow checker, there's one model that uses like a permission system to explain how it enforces its rules, and that's something we will take a look onto. Hmm. So why references in borrowing? So if you see this code, we have a greet function that takes a string and prints the string. A hello is missing here, or it's here. And then you have the main function where you create a string, call the greet function, and afterwards try to format the string in another way. Does that compile? What do you think? So it's probably, if somebody asks this question, it's probably not doing the compilation here because the ownership of M1 was moved down the scope to greet and never came out again. So what happens then is you get this value moved here, and I think there's no M2, so that's an it's a comment nonetheless. Value borrowed here after move. So we cannot borrow a variable or value after it has been moved. Is an error message for that. And with the things we know so far, and we also saw that earlier, what we could do is like call a function, move in a parameter, and later move it out again. And that's working. That's also it's even not slow or something. So the compiler does a good to get this fast, but it's not nice to write and doesn't look nice. And with references, which is like the next example, you can just borrow the variable for the greet function. And I think no,
Yeah,
there is
we
no
have a
error.
slight error here. There is no error. This is correct.
Sorry, that was a copy paste error probably. Um, so there's no error. And to now come back to this illustration model, if we start to use references here with the ampersand symbol, we get a pointer in the greet method that points to the element M1 or M2 on the stack. So that's actually what's happening here. We have yeah, references that refer to another variable. And this way we can yeah, access string in read-only to mode as many times as we wish. And so to just recap, this box T is an owning pointer to the heap, and references are always non-owning pointers to either the stack or the heap. So you can also have references on values or variables that are only on the stack. Um, yeah, I think last time we missed the example for the for loop, so I thought that's a good place to bring it in because actually dereferencing, which is like accessing the data behind a reference or pointer in C++. You do this too with the, I think, asterisk operator. And here in the example code, just wrote a method or function process until element, which gets this slice. If you recall the slice from the last time, but it's like an array and parameters stop at this specific element or element value. When you now iterate over the slice, you access references here. So you have to dereference element to compare it with stop at. So it's not, it's good to know that that's possible, but it's not, I don't think yeah, it's not happening too often, but sometimes. Um, so, mm, the next part is what is aliasing and what is mutation? Aliasing is really when you use different names or different variables to access the same data. And when we have this with mutation, we could run into a lot of problems and actually a lot of subtle bugs in um, native code, especially in multi-threaded environments, are because you had aliasing that is mutable. Therefore, this borrow checker really checks this either one unique reference or many read-only references. And now to have a more deeper understanding, there's a good example using the dynamically sized array vec. So here we define a
Oh,
mutable vector that has
we have a question. If you could go back to the code where you're passing a vec to a function, expecting a reference to a list.
that's sure.
Your process until here. Yeah, so here you're defining v as being a vector in your main function, and then you're passing it to process until element. And process until element expects a slice,
Mhm.
but v is obviously a vector, and these are different types. So I think you're justified in asking, how can this compile? Is this correct? And the answer is yes, this is correct because Rust has a notion of sort of one type kind of uh, being a pointer to another sort of type. So like in the sense that a pointer to an integer is can be used as the integer if you dereference it. Rust has this implicit mechanism for like automatically dereferencing types, and this can change types in particular ways. There are not very many ways this can happen, but generally speaking, a vector can be viewed as kind of containing a slice. Um, and the particular thing this does, we haven't got to traits yet, but there is a trait called deref. And because vector implements deref with a target of slices, this means that you can pass vectors like this to functions expecting slices, and they will just automatically expose their internal slice, and you can use it without thinking. Um, I can go into more detail if you have particular questions about this, but the long and the short of it is just that um, the uh, the vector like is transformed implicitly. Um, Not transformed in the sense of changing its contents, but like transformed in the sense of you just immediately get a different view on it.
Yeah, you can really think about that like with this marking for the copy, but with a bit more of deeper knowledge that you say, okay, this can be dereferenced in a slice, and then you write a function that does that, and then Rust can do this implicitly for calling functions and so on.
Yeah.
Okay.
But yeah, generally speaking, this happens with types that act a bit like pointers. So, a pointer to t implements deref target t. A box implements deref target t in exactly the same way. And you can think of a vector as kind of being like a pointer to a slice. And this is why it implements the after slices.
Okay. Okay, to come back here, like what we want to understand is why is this rule so important? And when you have like a vector with three elements and you get a reference into this vector, like to the last element in this case, and now you push, then you get this error message that you cannot borrow it as mutable because it is already at that place borrowed as immutable. And that's very interesting. And also, um, yeah, I think interesting is the right word. Like if you have like access internal data, you normally also change the permissions of the back, like this V itself. And why is it the case? So what could really happen under the hood? And when that would compile, what we would end up in the memory is before this line here, you got this vector that has a length 3, for example, on the stack, a capacity 3, and some pointer to location 1 that points to this data in memory. And then you have the reference that is also the pointer to this 2. So in respect to the location 1, after the push, internally, VEC has to reallocate the memory because it's not big enough. So the length changes to 4. The capacity, I think the standard heuristic is to double the capacity if you run out of size. And then you get a new location in memory. And the old one is normally, yeah, either deallocated or not accessible anymore, or could be used for something else. And in other programming language, these could be dangling around for a long time, be used in undefined ways. And in Rust, that cannot happen. And yeah, how do we really get lost a bit about the boat checker? How could we think about what it is doing internally? And there is this model of having read, write, and own permissions. So read means data can be copied to another location. Write means it can be mutated. And own means this data can be moved or dropped. That means deconstruct. And this permissions, they are only now a helper that exists at compile time. That's nothing happening at runtime. And when we generate a variable, A is 42, we normally get a read, no write, and an own permission for this variable. If we also want the write permission, we have to put a mute here. And these references can temporarily remove these permissions on the variables. And here is our example from before, but in a fixed way. So it's working this time, and we can together try to understand what this diagram means. So at the first line, we initialize the vec, and when we initialize it, because we're using the mute keyword here, we have all these three permissions, read, write, and own. And then we use a reference into the vector to the last element. And at this point, we lose the permissions write and own for we. We have a reference with the read and own permission. And we have a value like the dereference num has the read permission here. And important here that is a place. So we see his assignment, but there may be other places. because the Rust compiler knows the num reference is not used after that line, we can we can it changes the permissions at that place in the code. And here we
So for
gain,
clarity, what you're showing here is that the Rust compiler detects that this is the last place num is used, and so v
yes.
gets its permissions back because num is going away.
Mhm. So what is important here is like it's not related to a scope, but really to the last place it has been used. And the same occurs here. Here we is used the last time, and so the variable uses all its permissions. And well, in our previous example, we had we were um, we had switched both these lines, right? We had the push before we printed out the value, and now at that point for push we need the read and the write permission, and at that place we don't have write permissions for we. And yeah, for mutable references, so if you use a mutable reference as here, you also get the write permission on the dereference data. So what was making me curious when I was going through that, because when I was going through the Rust book the first time, there wasn't in there, and I think there was maybe it was like it is a fork in the end, so I'm not sure when it was published, but this really was strange. Why are there two lines, right? And here you really have permissions on a reference. Here you can read the reference, but you could also add a mute at this point, and then in the next line you could write num equals ampersand mute v1, for example. So you change the reference. And yeah, so there, there's a nice overview about typical ownership errors in this fork of the book. I did put the link here. So typical stuff that you may know from C++ is if someone returns a reference to something that is on a stack of a function. So that's not working. You may lack permissions in the function signature. And yeah, I I would like propose if you run into a particular problem, you could have a look there, or if you're interested, um, go check that out. Um, so the most important part is really we have this one unique reference or multiple read-only references, and that there's this read-write owned permissions model, and that they change at places. So that's not related only to assignments, for example.
Mhm.
And
I might also say that mutable and unique are different words for the same thing. They're not different types of reference. A unique reference is
yeah,
exactly the same thing as a mutable reference.
yeah, it's like a synonym, so to speak. Mm, yeah. And we all already saw in case of the WAC, if you get a reference of something that's inside the WAC, we also change the permissions of the WAC. And that is also true for fields of structs and so on. And yeah, maybe to come to more practical code, I would give a short recap on slices because with this diagram kind, it's easier to think about them. And then we will have a History 101 why slices is superior to the old way of APIs. Like in the older days, every API was working with just integer indices for string operations, for example. And the slice is more, let's say, intelligent type that bounds the array with this information. And if you think about a hello world string, you could use two references into other two string slices, which are encoded with this range signature. So that means this string um, from index 0 to index 5. And here at the bottom, you see, yes, we have a string. This points to the entire heap data. And hello, it just points to this substring here. And yeah, if we just use a reference, so a reference is a bit different than a slice, that will just point here from S2 to S. And so in this book, they also use this example of first word, and at that point, it started to add in some dependencies on an iterator API, but we will go through this step by step. So we have a function, first word, that gets a string reference and returns the use size. So at what point, at what index does the first word end? We can then convert that to a byte array and iterate over the bytes. So I mean, Python has iterator API, probably enumerate if you have seen it, if you're familiar, but if not, what actually happens is we get the index in the collection and the element itself. So it's a pair returning the index and the value or the reference on the element. And here we compare with a space. And if we found a space, we know at this index E, the word ends. So that's the so, last point, so to speak. And if we didn't find it, we return lang. But what are the problems with this? So let's have a look. When you now look from the Collie side, for Rust, using this kind of API comes with a problem that now we don't have information anymore. So we generate our string hello world here. Then we call first word, and when we call that, we have S with data on the heap and word, which is just giving us the index 5. And then, because there's no information, we could clear the string and still there's no information about that word is related to the string. And also, when you think about an API, sometimes you just got like one index for find, and sometimes you need for substrings you need normally two indices and so on.
We have a question about the loop in the previous slide, I think.
Okay.
Um, no, the loop does short circuit by returning.
Yes.
Like that short
So
circuits the loop.
that ends the loop and also ends the function.
And the B syntax there, you're not looking for a B. So this is some of Rust's particular uniqueness around strings,
Ah, mhm.
which is that so by default in Rust, strings are composed of UTF-8 code points, but they're underlyingly stored because, well, Unicode code points rather, but they're underlyingly stored as UTF-8, which is a byte-oriented format. So you can, if you want, whenever just reinterpret your Rust string as a sequence of bytes, although those bytes may or may not be, full characters. And in this case, what we're doing here is we're wanting to say, look for the first, ASCII space character. But by default, if you write a character, like with the single quotes in Rust, you get a Unicode character, which is 4 bytes wide. So we want our normal ASCII byte character. And the way you write this in Rust is by just prefixing a character literal with a B, B for byte.
Yeah. Yeah, this kind of suffixes um, are quite helpful to have literals that have specific types. Um, and so to come back to the example, like what would be a good or more idiomatic Rust implementation that would be using a slice as a return type and actually not too much more changes. So we index from 0 to I, but now if we would have like second word, for example, we could just have the same return type, which is cleaner from an API perspective. And the slice is now also coupled with the string here for the borrow checker, empowering like the Rust compiler can help you more if the types are more yeah, like say bounded and having their constraints encoded. And with that, we would get an error here. Actually, the println would output the word, but this code doesn't compile because of the clear and the permission mismatch. So here, because of this borrow, S is not right anymore. And that's true for as long as this word is there. This is yeah, this is how slices help here. It's a borrow checker. And yeah, I was just thinking about if you want to try some stuff yourself, you could come up with some task to implement to get some manual work done. So for me, I'm a more practical learner. I like to dig into the theory too, but normally if I learn, I learn that I maybe didn't understand everything so deep yet, and then yeah, doing the practical route is good. So just as a inspiration and yeah, what is a good type for TBA? That's a interesting question to research about and maybe have a discussion with us in the Discord if you're open to it. Right. Um, yeah, now this is actually quite long, but we announced that we also did do structs. I I'm hopeful that you are equipped to challenge the borrow checker with this theory background, and feel free to reach out over our Discord channel if you need some help. And now it's more light, right? Because struct, you have this concept in many programming language. Here, first of all, we have the typical um, type definition. Here I'm just using U32 for no specific region. And if you want to instantiate that, you can use this, I think, curly brackets and give fields initializers. And there's also a tuple struct. We saw tuples in the last week, and a tuple struct just gives you the possibility to have a real type name for a tuple. And that's how you declare it. Just a comma-separated list of types. And you can instantiate it in this way by giving it values. Then we have associated functions for structs. So in C++, you would have functions related to classes. Here we can relate them to structs. And this function is it's called square. It gets argument a or parameter a, and returns its like self is like a type itself. And then we just create a rectangle with both width and height BA. And if you want to call it, you use the double colon operator. And yeah, all these functions need to be part of an impl block for the rectangle. The cool thing is we also have like what you would refer to as normal methods in other programming languages, where you have either a read-only reference to self that may do some area calculation, or you could have a mutable reference to self that changes this instance. So here we say we want to double the rect, and we just multiply both width and height with 2. And in Rust, you can have several input blocks for the same type. So you don't have to put all the methods at the same place. But it's nice to know, but I think it makes most sense for the really big types. Um, and if you want to call this, so here we have some example for calling code. We stick to our square generation. We store the area of the rect. Then we double the rect, and we store the area in another variable. And then we can print out both areas. So 4 to square is 16 and 8 to square is 64. And the last kind of methods are consuming methods. And that is probably strange if you come from another programming language, because what you can do is like really you destroy your or move out your you move your instance into this method itself, and then anything can happen with it. So here, as an example, we just say, okay, we want to have a circle that is the that contains the rect completely. So we take the radius of whatever is higher width or height. And when we then use this code to circle, at that line, rect becomes moved out. And for this reason, this line would give you an error because of the moved out value. And this changes compile time properties of your data without reallocations. Reallocations are very, very um, expensive from performance standpoint. There's a question.
The answer is yes. If so, in toCircle, as self
Yes.
comes in, the rectangle is dropped at the end of toCircle.
Mhm. So when you what you often see is like the heap elements, like when this would contain a vect, you would move the vec into the other type and then um, keeps this memory alive. But at this point, what is nice to understand is really this superpower of Rust, how to think about the types. Because the Rust types, they encode properties and constraints for the compiler. And this empowers you to specify the correctness of your programs. Like I'm also running the Rust Dortmund meetup. And last time we had a talk of a guy who is a maintainer of UnitForge. This is a Rust library that ensures that units, like physical units, are calculated in the right way. Like if you have meters here and kilometers here, you cannot get the conversions wrong. This is proved at compile time. And that's what I mean with that. And the first example you already saw here is how slices as a type could empower the compiler to help you write correct Rust. And we will probably see more when you continue the journey with Rust. Um, yeah, with a new type pattern. So that is borrowing again. So um, and the question is if we generate a rectangle, we have a mutable reference to um, W. And
Did you intend it to be a mutable reference or just a mutable binding?
yeah, I think I did the code wrong, right? This needs to be sorry for that. Um,
Yes. So imagine this to be ampersand mute rect dot width.
yes.
Uh,
Sorry. So the this mute needs to be here. And yeah. So yeah, here actually it's I'm not sure why is it here. So that is the code you want to see, like referred to in the error message. Here you get a similar error as we already saw in the case. And yeah, I think that's a lot to take in for the start. And but with all of that, you're really well equipped to tackle Rust because that takes you quite far. What would you say, Cosmo?
yeah, I think we've gone through a great deal. A lot of this stuff is pretty heavy. Um, the uh, the kind of properties that Rust tries to guarantee for you are like very useful, but they do require this like really crisp sort of mathematical model of your program as it goes, and uh, often that is like once you've used a lot of Rust, you can just sort of have this sit in your head and it works very, very easily. But definitely, if you're encountering this for the first time, it's very easy for this to be confusing and sort of difficult to track and understand. Um, so yeah, basically, we hope that this has started you towards that, but it's very understandable if there are things you're not so clear on. I think we have a good chunk of time in which, if you wanted to ask questions, now would be an excellent time to do that. Um, so yeah. I'm desperately crossing my fingers that people are furiously typing in chat and I can't see it. But uh,
Um, yeah, I'm personally also like a quite practical learner.
mhm.
So what I think is very helpful if one runs into these problems to tackle them at that time too. So, but now you have a nice understanding of where you could have a look and maybe
Yeah.
look
Oh,
back at.
aha, we have an interesting question. Does Rust allow you to have private member functions or data members? The answer to this is
Mhm.
yes. Things are private by default in Rust. So if you have some struct, like the rectangle struct we gave as an example before, where you have, field one width, field two height, those structs, just as written, are private by default. And if you want them to be public, you prefix them with the pub keyword. So you do write pub with colon U32, whatever. Um, yeah, if we hop back, we'll have a nice example to work with. Yeah, here. So yeah,
Put pub.
uh, yeah, as written, width and height are private. But Rust has sort of an interesting model of how of where the kind of boundary of publicity is. Um, which is that it is at the sort of source file scope or the module scope, which are the same thing in Rust, largely. Which is to say that if you write this struct rectangle definition, and then immediately below it, you write just a normal function, global scope, like you'd write in C, and this function takes a rectangle. That function can access width and height and edit them and read them and so on and so on. But if that function was defined in a different file, it would not be able to access them. And so this kind of property is this nice medium where so Rust really encourages writing, for example, tests in the same source file as you define your types. And this means that all of your tests can just like automatically go in and mess about with your private fields and test that they are what you expect them to be without breaking encapsulation. Um, and yeah, so it's the same story for functions as well. So by default, if you write a function, it's private, and if you want it to be public, you have to prefix it with the keyword pub. Um, and there are slightly more nuanced modes of this. So you can have things be public only to the current crate, or public only to the super module, or things like this. But these are sort of beside the main point, which is that things are private by default and can be marked more public if you need them to be.
If you come from a C++ background, you could think about like every type in a file is a friend of each other, but only for this file level.
Yes, exactly,
It's
exactly.
very helpful. Yeah, if you think in modules where, especially in Rust, you have many types that yeah, are more related to each other. Yeah.
Yes, yes. A great deal of work has gone into it. Um,
Uh, I wonder, what resources are you using at the moment for your learning journey? Is it like the Rust book, the Rustling course, a mix? Would be quite interesting for us to know from our perspective.
yeah, particularly as like if it'd be very good if some people don't know about a resource and you're using it. It'd be good to know.
Yeah,
Um,
actually, like this Brown University fork, I wasn't aware of it, and ownership is a bit more, um, verbose or deep.
oh, fantastic! That's a tasteful choice.
I've been going through the book Rust in a Month of Lunches, and the author has this repo that I'll just put it in the chat here. And he also has gone over the book's based on his video recordings, and the video recording also covered the same content of this GitHub repo. So the book by Manning is just a formalized version of this repo and the video recordings.
Nice. This is actually something I'd not heard of. This seems cool.
Yeah, didn't know it either.
One last thing I wanted to ask about the video recording, because I had to join late because I'm working at the moment from the States.
Yeah, of course.
Where would that be available from? Is this also going to be on the YouTube channel or
Yeah,
someplace else?
I think things are going to be on YouTube. In particular, also the previous one also recorded, but is not yet on YouTube. Should be within the week, I think. I'm right about that, Tim?
Yeah, that was what I hit.
Yeah. Okay. No, in any case,
Um,
that's the goal, if not the truth.
that's check.
But yeah, thank you so much. I've been using the pause iteration videos as well while I'm covering the book. So this is just like revision upon revision upon. So this is all very helpful. Thank you.
Nice, nice.
So I just put the YouTube channel in the chat too. If you're not, I like if you're not subscribed, maybe then you get at least a notification.
Mhm.
And there are some, yeah, there's some videos like this meetup is running for some years, right? Right.
Yeah, cool.
Then I would say if there are no questions anymore. Hopefully we see each other in like 2 weeks.
Yeah. Yes, yes. In 2 weeks' time, I'll be talking and we'll be doing pattern matching, as said before at the start. Um, yeah, I'm excited.
Yeah.
Well then, yeah, cool. Perhaps we will be saying thank you for coming and goodbye.
Yeah. Thank you for coming.